Okay, so let us wait for a few more minutes if anyone comes, and then we can start at say probably 6:10, 6:12, something like that. Let us wait for some time. Okay, so hello and welcome everyone to the live session of Fundamentals of Protein Chemistry. And today uh, we would be discussing on the week 4 lectures which were taught to you. And this is a live session, so here we will be discussing the lectures in brief and discussing with you people a few questions which will help you in solving the assignments and taking up exams which are going to happen in the near future. And I am Srijan Sen, and this course is taken by Professor Shagota Dasgupta. Welcome all. So I am sharing my slides with you people. Kindly confirm if my voice is audible and if my slides are visible. So is my slide visible to you people? Kindly if anyone of you can confirm, and if my voice is audible enough for you. Can anyone of you please confirm if my screen is visible and if I am audible?
Your voice is breaking, sir.
Okay, I'm trying. Okay, probably there is some technical problem, or maybe the network is not good over here. But we can start. Okay. So in today's lecture, so in the previous lectures, we talked about the amino acids, then the proteins, and how can we purify these proteins, and then we discussed about the structure of the proteins, about we discussed about the peptide bonds and all. So in today's class we would be discussing about protein isolation and purification. So today's class will be mostly focused on how can we isolate proteins and in what manner can the proteins be isolated and then after isolation process how the proteins can be purified to get a pure form of the protein. So beginning with the isolation of the protein, so if we see that proteins can be isolated from different sources. One is the natural source and the other one being the recombinant source. Okay, so from the natural source, like there are plant extracts, there are yeast extracts, and there are bacterial proteins which can be extracted by the natural means. Whereas on the other hand, there are the recombinant proteins which we engineer. So these are called the engineered proteins or the recombinant proteins, which are expressed in the different sources. So like you say in the prokaryotes or the eukaryotes, depending on the type of proteins that you require. So we have to keep in mind that the proteins can be isolated from two ways. One is the natural process and the other one being the recombinant source. So what are the different natural sources which are available to us? One includes the whole organism we can use. There can be certain tissues which express proteins. Then there are the embryos, the tissue culture cells, and the microorganisms. These are the natural sources which actually from where we can isolate the proteins. The other form being the recombinant means, which includes your plants, fungi. Then there are other microorganisms, mammalian cells, then insect systems. So there are different model systems in which we can express our own protein of interest or the engineered protein. So this is via the recombinant means. So one is the natural source, and these are the natural source falls under the category of the natural sources, and these are the via the recombinant means. Now there is a general strategy of protein purification. So this is, you know, that this is a cell where you have the different organelles and the different layers of the cell which are present inside it. So the first one being that what is the general strategy behind this protein purification? It is that you have a tissue or a microorganism and which expresses a particular protein, and then what happens is that you have to disrupt that particular organism or that particular cell. So after disruption of that particular cell, the protein then comes out. So after the protein comes out, it comes out in the form of a crude extract, or you can comes out in the form of a crude extract. So this extract now we have to undergo the crude fractionation. Okay, so where we have to remove the unwanted crude products and we have to get our own protein of interest, and from that we have to find out what is our protein of interest. Now from the crude extract, after we separate from the crude extract, there will still be some impurities which remain, and therefore we have to remove that by selected fractionation. So from protein isolation, this is the general strategy of how we can purify the proteins. Now there are different protein isolation methods which includes your salting out strategy, or when you add a lot of salt in it, then what happens, it the protein of your interest precipitates out and you can isolate the protein. The other forms being your centrifugation, then chromatography. So among the chromatography, you have the different categories of chromatography. One is size, which depends on the size and the mass, which you can call the molecular sieve filtration. Then you have the charge. On the basis of charge, if you are isolating the proteins, then you have the ion exchange chromatography. Then on the basis of hydrophobicity, if you have to separate them, then there are reverse phase chromatography, then the hydrophobic interaction chromatography. And on the basis of affinity, if you are separating them, there you have the affinity chromatography, and then you have the antibodies which you can use for the isolation and the for the isolation of your protein of interest. So these are the mainly the techniques and a general basis as to how proteins can be isolated. And this is not only the isolation strategy, you can also use this strategy on a tandem basis for the purification of your protein of interest as well. Now what is the selective precipitation? So selective precipitation is mostly based on your ionic strength, and the ionic strength, then it includes the pH. So you are selectively precipitating it. So why does a protein precipitate? Because when a protein protein comes very near to its pI value. So if the pI value of a protein is very close to the pH of the buffer or the system that you are using, then the protein precipitates. So how can you selectively precipitate it? Not all proteins have the same same pI value. So depending on that particular pI value, you set the pH of the buffer in such a manner that you can separate it, such that you can precipitate it. And after you are done with the precipitation, you can isolate that protein of your interest. Then you have the ionic strength on the basis of the salting out and the salting in procedure. Then you have different organic solvents by which you can actually precipitate it down. And the third one being the use of polyethylene glycol or molecular overcrowding agents. So the selective precipitation is mostly based on the specific property of the target protein, among which you have the charge or the hydrophobicity and the solubility as well as the size. Now coming to the salt fractionation, what does it say? So if you from the graph, if you see that there is the salting in and the salting out effect. So what is actually occurring over here? So there at very low salt concentration, the protein is precipitates out. Okay, so the protein is supposed to precipitate out, and when you're increasing the salt concentration, you see that the solubility is increasing, and it increases to at a certain till a certain extent, and after that, what happens? The salting out phenomenon occurs, where there is mostly your salt concentration is very high, and it prevents the protein molecules to be in contact with your water molecules, and due to such intermolecular hydrogen bonding and not the intramolecular hydrogen bonding with the water molecules, the protein precipitates out. So very high salt concentrations decreases in solubility as the ionic strength increases, and this is called as the salting out effect. Whereas there is a mild increase in the salt concentration, that is at low ionic strength, the solubility increases, and this is the salting in effect. So when at very low salt concentration, when you are increasing the salt concentration, the protein first becomes soluble, then at after a certain threshold value, the protein starts precipitating out, and that phenomenon is known as the salting out. Now there are some ions that are more effective than the others in affecting your protein solubility, and now this is based totally on the Hofmeister series. Now there are several cations and anions which in combination with each other forms a either you can tell a salt which precipitates your proteins, or you can say a salt which increases the solubility of your proteins. Now these salts actually affect in two ways. One is it enables the protein to precipitate out, or the second thing being it allows the protein to solubilize itself. So it enhances the solubilization, or it decreases the stability of the protein by increasing the salt concentration and precipitating the particular protein of interest. Now if you see the Hofmeister series, which I did not mention over here as such, but if you see from the two arrows, you can understand that what is actually happening. So from the cation perspective and the anion perspective, two things happen differently. Now if you see, as you move from vanadium to ammonium, so in this direction, when you're moving, it is adding to the stability of your protein, but at the same time it is salting out your protein as well, that is your protein is precipitating. However, if you see from the anion perspective, as you move from the sulfate towards the thiocyanate, so on moving in this direction, your protein is undergoing the salting in effect, but at the same time, it denatures your protein. So because of the denaturation of the protein, your protein solubilizes. Okay, but does not, you cannot say that it stabilizes. When it denatures, it solubilizes, but it does not stabilizes, whereas the salting out effect actually stabilizes your protein, and this can often lead to precipitation of the protein, because as I mentioned previously, because of the intramolecular hydrogen bonding with the intermolecular hydrogen bonding with the water rather than the intramolecular hydrogen bonding. Now, what is the mode of action of these phenomena? Now, if you see high concentration of small, highly charged ions, such as your ammonium sulfate, competes with the proteins to interact with the water molecules. And when they compete with the water molecules tend to interact less with the surface of the protein molecules, and this leads to your precipitation of the protein, or your protein tends to come out of the particular solution. Now, water is removed from the protein solubility. Now, is removed from the protein surface, and the solubility decreases. That results in the precipitation. So, by this mode of action, or by this mechanism, you can tell that your protein is salting in or salting out. So, and the previously mentioned Hofmeister series actually tells you what combination of salts or cations and anions should you choose, such that you can precipitate out your protein, or solubilize your protein, or you can say stabilize your protein, etc., etc. So depending on what you want to do and how you want to separate your proteins, you can use the different variations of the um, salt mixture, or the cations and the anions of the ions that you're using. Now, coming to the technique by which you can isolate proteins as well as purify proteins. So this is known as the centrifugation technique. It has been previously used several times, and this is the oldest method of separation of your proteins, right? And what happens is that in a centrifuge, you have an armored chamber, then you have the material or the protein, or the entire juice that you want to, from which you want to separate your protein out. And there are two types of centrifuges which you can mostly observe. One is the rigid rotor centrifuge, and another one is the swinging rotor centrifuge. So the rigid rotor, you will see that the rotors are fixed over there, and there is a fixed angle between these rotors, and you would see that the material is sedimenting on the sides of the um, say the sides of the tube in which your solution is there. Whereas in the swinging rotor, you will be seeing that the entire material is at the bottom, not on the sides, because it has a flexible angle, and mostly the angle between the two rotors is 180 degrees. So in some cases you need to use the swinging rotor, whereas in the other cases you need to use the rigid rotor. So depending on how you want to separate and do this, so you can use the different kinds of rotors, and also on the capacity of the rpm of the speed, like you have the so like you have a protein of heavy molecular weight, and then you use a rigid rotor, whereas of a low molecular weight you use that. So depending on what you want to use and how many materials you want to separate them, you can use the different kinds of centrifugation techniques. Now, many cell fractions are done in the swinging arm rotor, because there is not the pressure of the sediments on the wall. Rather, the sediments tend to be at the bottom of the tube, right? Now, so the metal buckets that hold the tubes are free to swing outwards in the rotor turns, and there is a cell homogeneity before centrifugation. After that, you get a supernatant and then the pellets. So the smaller and the less dense components tend to be on the top, and the larger and the more dense components tend to settle as pellets. Okay. So now what happens when, say, you disrupt a cell and you want to separate out the different components from the cell. Say you want to separate ribosomes, then say the nuclei or the mitochondria. Sometimes you have to separate the microsomes, peroxisomes. So for that, the different speeds of centrifugation needs to be used. So what happens is that when you are centrifuging it at a low speed, say about some particular RPMs and all, okay, but it is at a very low speed. So what happens is that at low speed you can only get the whole cells and the nuclei and the cytoskeleton. So if you see, when you're centrifuging at a low speed, you can only separate the molecules like your whole cells, nuclei, and the cytoskeletons. Now, when you are subjecting this cell homogenate, say now after you get the pellet, you take the supernet and you spin it at a medium speed. Now, on spinning it at a medium speed, you can separate out the mitochondria, lysosomes, and the peroxisomes. Now, after then again you get the pellet, you separate them, and then you again spin the supernet at a large speed or say a high speed. Now then the pellet will contain your mostly microsomes and the smaller vesicles. Now in the last stage, when you are centrifuging it at a very high speed of say very high speed, okay, the supernatant is subjected to a very high speed centrifugation, then your pellet will contain the ribosomes, then there are some viruses or the larger macromolecules. So in this manner, by modulating or manipulating the speed of the centrifuge and the cyst or the solution which you are centrifuging, you can actually separate the different organelles or the different components of a cell, and on the basis of this you can separate out different things, and now on subjecting them to at different speeds, you can separate the components that you would be requiring. So keep this slide in mind, because there might come a few questions like what are the components that you can separate after you subject your solution to a medium speed. Then you have to mention it's the whole cell nuclei, then you have the cytoskeletons, the peroxisome, the mitochondria. Because remember one thing, now as in the tandem way you are separating them, it is possible, but if you are separating them in the primary stage at high speed, then you would get all the components. Okay, so now if it is given that your sample is subjected to a very high speed, so what are the components that you expect? So you have to mention small vesicles, microsomes, along with your peroxisomes, mitochondria, nuclei, cytoskeleton. So everything would be there. Okay, so just keep this thing in mind as to. So this also actually tells you about the size of the um, components present inside the cell. Now this is the principle behind your centrifugation and your sedimentation. So the ultracentrifugation techniques uses the finer separation and the less convective mixing using your density gradients, where you use sucrose and your cesium chloride. So these are the two solutions which you use for the forming a gradient, because cesium plus is a very high, um, means it is the biggest cation, and Cl minus is the smallest anion. So that is the reason you use them. Now there are other sedimentation techniques like your velocity sedimentation, equilibrium sedimentation. So what is this sedimentation? So it uses the centrifugal force, which is your omega square Rm, where R is the distance between the rotor and the center of the sample tube. So between the center of the sample tube and the rotor wall, the wall of the rotor is your R, and M is the molecular mass. Okay, so there is a centrifugal force which is acting, and also you have the buoyancy force, the frictional force, and the diffusion which also occurs. So your buoyancy is minus omega square r m naught, which is the displaced mass, and the friction is minus fv, where f is your frictional coefficient, and the radial velocity. So if you see that there is a force which is acting towards the wall, and there is a force that is acting away from the wall. So if you see that what is acting towards the wall, that is towards the bottom of the wall, it is your centrifugal force or the Fc that is acting at the base of the tube or the bottom of the tube. And there are other two forces that tries to nullify it, that is your frictional force and the buoyancy force. So these are the two forces that counter your centrifugal force. You do not have to keep in mind about these equations and all, but keep in mind about the different forces that is acting on a sample when you subject them to the phenomenon of centrifugation. Now coming to the recombinant DNA to purify the protein, so you have a particular DNA which you need to clone it, and then you have a expression vector. So it can be an expression vector or a cloning vector, that does not matter. So this phenomenon is totally termed as your cloning, where you have a particular sequence of your interest or a gene of your interest that you want to incorporate inside your vector, or say a cloning vector only, and then you can transform it into an expression vector. But say you have a particular gene of interest. Now what you do, you clone this DNA inside the vector, and you get, so as of now you have the gene of interest or the DNA. So the gene of interest is your DNA material that you want inside, that is going to be transcribed and further translated to give you the protein of your interest. Okay, now what happens, this gene of interest is now put inside your expression vector, and this entire system becomes your recombinant DNA plasmid. So how do you join these DNA and the expression vector? So there are different say overhangings, like there are blunt ends and there are sticky ends. So these ends are the ends on the DNA as well as the vector helps are joined together with the help of the DNA ligase. So after the ligation process, you get the recombinant DNA plasmid, and now this plasmid is transformed into the bacterial cell, and then inside that cell your protein is expressed. Okay, and after the expression of your proteins, you lyse the cell and you get the protein, and then you can perform different assays with the protein of your interest. So this is the way of how you can clone up your or transform your recombinant plasmid or your engineered plasmid inside the bacterial cell and get your protein of interest. Now there are different bacterial protein expressions, like there are expression systems like your PET vector, the P dest vector, you have the PMOL vector, PJEX vector. So there are the different kinds of expression vectors. So why are we calling them expression vectors? Because it has the, say, a viral promoter or viral promoter site, as well as it is capable of producing a viral promoter that viral say polymerase that goes and binds to the promoter site and transcribes and translates your protein. And now you have, for the eukaryotic vector system, you have the PPIC, which is of the yeast, then you have the baculovirus, the mammalian cell, or the PED vector. Okay, along with that there are different host systems inside which, so these are the different expression systems. There are other host systems in which also you can produce your protein. So those are the prokaryotic cells, like your bacteria, which is the E. coli strain of bacteria. Then you have the S. cerevisiae of the yeast. You have insect cells for viruses. Then you have the HEC93 and other cancer cell lines for when you are doing the cell culture or the mammalian cell culture to get your protein. So what you do is you have the host cell with your recombinant plasmid, then you express this particular protein, and then you harvest those cells. The harvesting of cells means you lyse the cells, you take the protein out and purify them to perform the different assays. So now okay, so when you have this particular host cell with a recombinant plasmid, what happens, you grow them in a particular medium. So you can use the lurea broth medium or the M9 medium, that is the minimal medium, to avoid any kind of stress conditions to your bacterial system for better growth of your proteins. Okay, so those are the minimal conditions which are required. So you remove the stress conditions which a system might face when you're using the LB broth, LB medium or the lurea Bertini broth medium. Okay, so these are the two components, that two systems that we use. There are other broths or growth mediums that we can use, like the tellurium broth and all, the TB broth. Okay, so there are other growth mediums. So we grow these cells in that particular system, and then after the induction of an IPTG, we give it. So we get that protein of interest. So what we do is we give the growth of these plasmids or the cells overnight in the bacterial culture. Then we inoculate it in a fresh medium the next day, which we call as the secondary culture or the 1% bacterial culture. And after we get an optical density where the cell population or the cell density is about zero point 0.4 to zero point 0.8, then we induce IPTG. So IPTG is an expression system. It is not an expression system, it is an inducible system, and what it causes is that it's a mimic of allolactose, that is, which is a lactose metabolite. So what happens when when you do not have IPTG and there is lactose, so it goes and binds to the, so you have the repressor system somewhere, and lac I repressor, and the repressor goes and binds to that system, and when the repressor is bound to your lac I sequence or the lac I promoter, then what happens, the RNA polymerase cannot bind to that particular region, and your protein expression stalls. But what happens when you have an IPTG, it is a mimic of the allolactose. So what lactose does, it goes and binds to the repressor system, and it does not bind to the lac-I portion, and the RNA polymerase can bind to the operator, and the protein expression is continued. So IPTG actually is an inducible system. So when you need to express your protein, only then you use IPTG for the production of your protein of interest. So it's a molecular mimic of allolactose, and which is a lactose metabolite. It is not part of any metabolic pathway, and it triggers the transcription of the lacoperon. So lacoperon, because it's a lactose operon, and it is an inducible system where the lactose or the allolactose goes and binds to the repressor system, binds to the repressor molecule, which does not bind to the lac-I promoter sequence, and the RNA polymerase can continue with the transcription pathway. Okay, so after you induce it with an IPTG, what happens? Your protein starts expressing and growing inside that growth medium, and then you incubate it either overnight or at 37 degrees centigrade for certain hours, and after that you harvest the cells. So harvesting is the process where you centrifuge your cells at high speed and you get the pellet, after which you dissolve this pellet in some buffer condition, which you call as the lysis buffer or the harvesting buffer. So in the buffer you keep that, and after that you can lyse this cell, sonicate it, and proceed for purification strategies. Okay, now coming to the purification of proteins. So purification of proteins can be done in several ways. One is the differential centrifugation. You have the differential salt precipitation, you have the solvent precipitation, preparative electrophoresis, and the column chromatography. So coming to the differential centrifugation, which I was just mentioning, and I mentioned it previously, nothing else to mention, where you separate the proteins on the basis of size, mass, and the density. So it is the function of the size of the protein and the speed of centrifugation, and it gives us a rough separation. It is basically just separating them on the basis of these above mentioned parameters. So when you centrifuge it at a low speed, you get some components. Then when you centrifuge it at high speed, you get the others. And in this manner, you are actually fractionally separating them, or you can call the differential centrifugation. The other form being the dialysis. So it is based on basically the osmotic pressure, and it allows you to actually get rid of the salt ions. Okay, so you can actually get rid of the salt ions and the smaller molecules that, or certain small molecule impurities that are inside your protein of your interest, right? Although it is understood that it is not possible to remove the salts completely, because you know that dialysis, in case of osmosis, that there is an equilibrium between the system and the dialysis bag, the material inside the dialysis bag. Now what happens is that when a certain salt concentration becomes equal to the outside and inside, then there would be no change of any ions. So there can never be a perfect zero or a perfect 100% condition, we all know that. So therefore it is impossible to completely remove the salts. So what this dialysis does, it starts, it gets rid of the small molecules, you can say the salt ions and everything, and you can also, it also helps you to uh, so it also helps you to uh, give entry to certain salts that might increase the solubility of your protein and all. So we might need to dialyze these proteins in different conditions such that we get we get proper understanding. We can perform different assays. So this is all about dialysis, which works on the principle of osmotic pressure. Now coming to the technique of column chromatography. So this is the most commonly used approach for purification of large amounts of proteins, and this technique can give you a high level of purity in large amounts, and also it requires lower efforts and does not damage your protein product. And this is the standard method for pharmaceutical industries for the purification of proteins, and it is used by the industries as well as the pharmaceutical companies for high yield production of your proteins in large amounts. Okay. So among these column chromatography techniques, we have techniques like the gel filtration technique, the ion exchange chromatography, and the affinity chromatography. So if you see in the gel filtration chromatography, there are different sizes of the beads. So and you pour the entire so there are porous polymer beads, and you pour your protein sample in it. Now the protein mixture is added to the column containing your clothing polymer, and then it passes through the column, and the protein molecules separate by size. So the larger molecules pass more freely, and it appears in the uh, earlier fractions compared to the small molecular weight proteins that starts eluting in the later stages. So what is the reason behind it? So there are pores, and the larger molecules cannot enter all the pores, whereas the small molecules can enter all the pores. Just a minute. Okay, so what happens? So the larger molecules can enter all the pores, and takes a long the larger molecules cannot enter all the pores and hence elutes faster, whereas the small molecules can enter all the pores and elutes at a slower rate. So you can see it from here that so you separate the molecules according to their size as they pass through the hydrophilic polymer, and this polymer beads composed of the cross-linked dextrose, which is tightly or uniformly porous. So the polar molecules, the large proteins comes out fast because they cannot fit in all the pores, and the small molecules comes out later because they get stuck in all the pores. So you need to have a way to know where your protein is. So you need a molecular weight marker, and you add a target to your particular protein. So if you want to purify an enzyme, add a substrate to the tubes where to see where it appears. Then you have the ion exchange chromatography, where you need to separate the proteins according to their charge. So you have the cationic substrates and the anionic substrates, and the proteins. So if it's a negatively charged protein, it gets um, attached to your or bound to your cationic pores and all. And if it's a negatively charged, it's the positively charged protein, then it binds to the negatively charged porous area. Okay, so say you have a mixture of positive and negatively charged proteins, and beads of positively charged DAE cellulose is there. So as these are positively charged DAE cellulose, so the positively charged proteins would just elute faster or in the void space, whereas your negatively charged proteins will bind, and after you use certain elution buffer or eluents, after that your negatively charged protein starts eluting. So this is called the anion exchange chromatography, whereas the other one, the reverse system, in which you have the cellulose, that is your carboxy, some carboxymethane and all, methylene. So there you have a negatively charged cellulose beads. The beads are made up of negatively charged cellulose, and you have both the proteins of positively and negatively charged, and when you pass them through these beads, only the positively charged protein molecules will bind, whereas your negative charged molecules comes out in the. But so on the basis of this, you can separate out the proteins according to their charge. So in the previous one, we separated the proteins based on size, and in this one, we separated the proteins based on charge. In the third type, this is affinity chromatography. So affinity chromatography can be performed in many ways for the purification of your antibodies, or you say some particular proteins, some proteins with different tags, and these tags actually have high affinity for some compounds, say your streptavidin, avidin, then your GST tag, then your histidine his tag. You have the nickel NTA chromatography, you have antibody, then protein, you have protein A, protein G along with immunoglobulins. So there are different affinity chromatographic techniques. So this is an absorptive separation in which the molecule to be purified is specifically and reversibly binds to a complementary binding material. So specifically it has to bind because the binding process has to be tight enough, but not very tight enough, because you have to after all elute it, because the elution process is also very important, because if you cannot elute it, then it makes no sense. So it should be such that you can elute it at the end of the day. The binding should not be very tight like your streptavidin biotin. Okay. So therefore, this process is very important and highly specific proper technique, and purification is 1,000 times better from a single step. And this method is used if you have certain linkers or tags which bind specifically to different compounds or to different ligands. So the protein is not covalently bound to the ligand, and see, you have a matrix, then you have a linker with an amino acid, and this binds to the phosphate groups. So these phosphate groups are playing a role in the affinity chromatography. Okay, so from the column chromatography, there can be a lot of questions, and you can expect numerous questions as to how and regarding the techniques about the size, SCC, then your protein is in a particular buffer, and how can you separate out the protein. So when I will be discussing the questions, I will be telling you. Okay, so this is all about the column chromatography, where we had the SEC, IEX or the ion exchange chromatography, and the affinity chromatography. Okay, so good. So let us take some break, and after that we can restart, and we have only a few things other than this to discuss. After that we can discuss with the question answers. Okay, so let us take a few minutes of break, and after that we can start again. So let us discuss the last few things that is left behind. So coming to isoelectric focusing. So isoelectric focusing is the technique by which you separate out the proteins based on the pi or the isoelectric point. So isoelectric focusing is focusing on the isoelectric point of that particular protein. So different proteins have different isoelectric points. So based on that, you put this protein in a particular buffer, and depending on the condition of the buffer, your protein would either contain a negative charge or a positive charge on the buffer condition or the surrounding sample, surrounding solution, and on the basis of this, you can separate out the proteins. Now, see, um, now you have to keep one thing in mind: when the pH of the buffer is greater than your pi, your protein will be negatively charged. Whereas if your pH of the buffer is less than your pi, then your protein would be positively charged. Now, if your protein is positively charged, that is when the pH is less than your pi, then it will move towards the uh, cathode, and if your protein is negatively charged, it will move towards the anode. So that is the entire thing about isoelectric focusing. Another thing is the polyacrylamide gel electrophoresis. So this can be of two types. One is the SDS polyacrylamide gel electrophoresis, and the other one being the native or the non-denaturing polyacrylamide gel electrophoresis. So both of these can be used to understand the molecular weight of the protein or the size of the protein. So electrophoresis separates protein based on the size using the electrical current. Okay, so this is based on the largest to the smallest, and then you are separating them based on the size of the protein. Now, for a denaturing gel or an SDS, which is the sodium dodecyl sulfate gel electrophoresis, in that case, you use a detergent for denaturing your protein, and then your protein contains a uniform negative charge, and it has that particular charge on a whole, and this will actually help you to separate out your proteins. Whereas for non-denaturing conditions, you do not use any kind of detergents, right? So for that case, what happens, even if your protein is in a higher molecular weight or is in the form of polymers, it is say tetramer or trimer, it is forming a trimer or a tetramer. For that case, it becomes difficult in SDS page to understand. But for when you're running a non-denaturing gel, then it becomes much more easy, right? So therefore, these are the two gel electrophoresis, and the gel electrophoresis is used for separating out of proteins based on the size. The other one being the preparative electrophoresis or the 2D electrophoresis. This is the combination of your isoelectric focusing and the SDS or the page. Alright, so firstly you separate out the proteins based on their pH. Okay, so that will also help, because sometimes if you are isolating proteins from a crude extract, okay, then it becomes very difficult to understand whether the protein is in the trimer, tetramer, or in what form it is, your protein of interest, right? So for that case, first you have to isolate the proteins based on their size, and based on their pi. That is, you perform isoelectric focusing, and then you cut that particular say matrix out, and or the particular gel out of it, and then you place it in a electrophoresis system or an electrophorese apparatus. So after that, when the proteins are separated based on their PIs, then you would get something like this. You have separated them, and then you separate them out based on SDS space. So you would be getting some peaks like this, where you can understand that this is your protein of interest, so this is your protein of interest, which one is your protein of interest. So you can perform in this manner, you can perform 2D gel electrophoresis as well. Now if you want to perform a say 3D gel electrophoresis, then you separate the proteins based on something else, and then you perform isoelectric focusing and then say SDS page. So there are three different techniques which you combine to understand your protein of interest or a particular engineered protein. So this is totally a theoretical part. Now let us discuss the problems. So as I discuss the problems in very interactive manner, so you are the people who are going to answer me in the chat box, and then I would be discussing with you the question answers, right? So so it's ready, and I want every one of you to be prompting answering me and be active when answering. Everyone's participation is expected because it's nothing but right answer. Okay, so the first question says protein separation techniques are often based on the following properties: solubility of protein, viscosity of protein, charge of protein, specific binding affinity of the protein. Answers in the chat box. So what do you feel should be the correct answer? Quickly, we have a lot of questions. Think and answer. So which of the following techniques are properties of a protein you feel is sufficient for the separation of proteins? So the first option, it says solubility of the protein, which is important. The next one is your, yes, tell me. If you have any queries, tell me. So see, the option C. Okay. Any other answers? Okay. So see, so the first option, it says solubility of the protein, which is important. Now the next one, which is the charge of the protein, we also saw that property is also very important. So 1 and 3 are correct. So where 1 and 3 is there, number 4 is also there. So C, specific binding affinity of the protein, that is also very important. But protein separation techniques do not include the viscosity of the protein. So therefore option C is the correct answer. Okay, now the next question. First step in two-dimensional gel electrophoresis generates a series of protein bands by isoelectric focusing. In the second step, a strip of this gel is turned 90 degrees, placed on another gel containing SDS, and electric current is applied again. Now, what happens in the second step? The individual bands becomes visualized by interacting with the protein-specific antibodies in the second gel. Proteins with similar isoelectric points become further separated according to the molecular weights. The individual bands become stains so that the isoelectric focus pattern can be visualized. The proteins in the band separate more completely because the second electric current is in the opposite polarity to the first current. Now tell me what would be the answer of this. So the question which it says that in 2D gel electrophoresis, first you separate on the basis of isoelectric focusing and the secondly on the basis of SDS, gel electrophoresis. So what happens when you place that strip of gel on an SDS page apparatus? D, the proteins in the band separate more completely because the second electric current is in the opposite polarity to the first current. Okay. Any other answers? Answers different from this? D. Okay. Okay. So B, D. Next. Next. Anyone else? Try answering. Everyone. Try answering. We have only few people. Everyone should answer. And if you have any problem, you should write me in the chat box because it is one of the two. Either you can answer it correctly or you have a problem in understanding the uh, concept. Okay, so if you see what it tells, okay, so if you see what it actually tells, so in the first step, you are separating it on the basis of the PI of your protein. That is clear because you are isoelectrically focusing it. Now, when you place it in an SDS page, so you separating a protein on the basis of its size or its molecular weight, right? So, in an SDS page, you have the proteins running towards the positive electrode because your proteins are negatively charged when treated with a negative or an anionic detergent. Now, what happens is that so your proteins having the similar isoelectric points will be in the same place. But when you are separating it in an SDS page, the proteins even of a different size or molecular weight can be can have a particular same PI. Okay, so now when your PI is same, they might not have the same molecular weight, so you will be separating them according to their molecular weights. You are not applying any antibodies which occurs in the case of Western blot or Western blotting or Southern blotting. Northern blotting, those are different. Antibody treatment is not done here. You do not want to stain after the isoelectric focusing to visualize it, and also the current is not in the complementary direction. So the correct answer is B over here. Because firstly you are separating it based on PI and then you separate it based on size or the molecular weight. That's why the proteins with similar isoelectric points will be separated according to their molecular weights. The next question, which of the following elements is a micronutrient for bacterial growth? Is it calcium, cobalt, nitrogen, or carbon? This is a direct question. So, anyone else wants to answer? Okay. So, if you see that among the macronutrients, because what are macronutrients and micronutrients? So macronutrients are mostly needed by the bacteria to operate its to create its functional proteins and all. So if you look back, that proteins require carbon and nitrogen mostly. Okay, so those are falls under the category of macronutrients because your proteins are mostly made up of carbon and nitrogen only, and then you have different side chains, and there are different divalent cations which actually enhance the entire process. So among the divalent cations, you have calcium, magnesium. So the micronutrients is the cobalt. So C is the correct option. And the others are macronutrients. Okay, question number 4. You know that the protein you want to purify from a natural source forms a multimer with multiple subunits. Given the molecular weight in solution much bigger than visualized on an SDS page. There is only a small amount of target protein in the total protein sample. Which of the following is an appropriate purification strategy? Affinity chromatography followed by ACC, IEX followed by ACC, and ion exchange chromatography. So the question just tells you that you have a protein which forms a multimer. That is, it is not in a monomeric state. So imagine it forms a dimer. Okay, but when you are visualizing it in an SDS page, you do not observe it. So what is the possible way you can actually separate it out? Okay, someone says it B, affinity chromatography followed by ACC. Anyone else? Okay, someone says A. I got an answer B. I got an answer A. A. Okay. Okay. See, so the molecular weight of the protein in the solution suggests that your ACC would be appropriate because it is forming something other than the monomer. So it is a dimer. Imagine. So, however, if you see that the filtration properties of ACC, um, it has particular properties to that of your um, ion exchange chromatography or the affinity chromatography. Now, if you see that here is another thing that is mentioned that your protein is in less amount. So, as your protein is already dilute, so large amount of large column would be necessary for purification to use your protein. Now, ACC, when you are performing an ACC, this also dilutes your solution a bit more. So you have to capture this protein in a very diluted state. For that, affinity might not be a very good strategy. Rather, if you are using an ion exchange chromatography, that would actually help you, because one, for the first thing being that it is a dimer or a trimer, it is something other than the monomer. And the another thing that it is actually uh, that your protein is very much diluted. There is not much amount of protein. So how much protein is there, you have to capture the entire thing. So for that, your ion exchange chromatography followed by SCC is the appropriate strategy that you should be using for the purification. So that's why A is the correct option. Affinity chromatography requires some good amount of protein. So for that, as the protein is dilute, you use ion exchange chromatography, and as your protein is in the multimer form, that's why you use SCC. So that's why A is the correct option. Now moving on to the next question. Okay. So which among the following statement is or are correct? Soluble proteins have high density and lower sedimentation coefficient. Nucleic have lower density and high sedimentation coefficient. RNAs have lower density and high sedimentation coefficient. Mitochondria has high density and low sedimentation coefficient. So you can answer this if you have a clear understanding of the differential centrifugation as well as sedimentation. They work hand in hand. Which of the following is the correct? Okay, so tell it's A. But the correct answer for this question is D. That is, only nuclei have lower density and higher sedimentation coefficient. So if you look back to my slides, whatever I mentioned in the differential centrifugation, you can understand that nuclei has a lower density, and that is why when you are actually centrifuging it at even low speed, it sediments faster. So it has higher sedimentation coefficient. Because of means it has a lower density, that's why it has higher sedimentation coefficient. But for the others, none of them are actually true. So that is why option D is correct. It is totally based on the size and the complexity. Okay, and also the sedimentation and the coefficient rate. Right. Okay. Let's go to the next one. Okay. This is question number 6. Wait. Huh. Yes. Tell me. What is A, B, C, and D? We discussed in today's class. Identify A, B, C, and D. Okay, anyone else? Okay. So B says DNA to be cloned. Okay, then expression vector DNA. Then we have the DNA ligase, and after the ligation process, we are getting a recombinant DNA plasmid. Very good. So that is only the correct answer. The next question. A mixture of three proteins of sizes 50 kDa, 30 kDa, 12 kDa are separated by ACC. In which order will they elute out? So which elutes faster and which elutes the last? Anyone else with a different answer? Yes, so higher molecular weight proteins elute faster and the lower molecular weight proteins elute in the last. So A is the correct option. Good. Okay, question number 8. IPTG. IPTG is added to a bacterial culture medium to induce protein expression. Which of the following is not true? It is a molecular mimic of allolactose. It is a part of the metabolic pathway. It triggers transcription of the lac operon. Which of the option is not correct? Say A. Any other answer? We have studied this, that it is a molecular mimic of the allolactose and it is an inducible system that actually is important for triggering the transcription as well as the translational pathway, but it is not a part of the metabolic pathway. So 2 only is the incorrect answer. So option A is uh, the option which is correct for this question. Question number 9. You have expressed protein in bacteria and lyse the cells. How will you check if your protein of interest is present in the cell lysate? So what technique should you use? SDS page, dynamic light scattering, measuring the absorbance, circular dichroism. So what technique will tell you that your protein of interest is present in the cell lysate? What does CD spectroscopy tell you? It tells you about the how well folded your protein is. It tells you about the secondary and the tertiary structure. What is the primary thing which you can do? You can just run an SDS page and then you can tell that yes, my protein of interest is there because you are getting the protein of interest in that particular molecular weight region. So on the basis of that, you can tell that I run an SDS page and I can get my protein of interest. Simple. But you have to go into such complexity. So others are not correct because it tells you about the complexity and the mobility, that is the randomness of your protein. CD spectroscopy tells you about the secondary and the tertiary structures of the protein. And 280 nanometer is for all proteins, so you cannot actually tell or differentiate between them. Understood? So SDS page run an SDS page. Okay, next question. In size exclusion chromatography, column matrix and solvent character selected to dash absorption, and dilution is done using dash buffer throughout the experiment. So fill in the blanks. Is it minimize, different, minimize, same, maximize, different, maximize, same? So what do you do over here? C, B, okay. Yes, so B is the correct option because the column matrix and the solvent are selected to minimize. You have to minimize the absorption, and you have to use the same buffer throughout your experiment to for the even the elution process during the loading as well as the elution time. So what is question number 11's answer? Proteins absorb at 280 nanometer due to the presence of which amino acid? B. Okay. Any other answer? Everyone is accepting to B. Why C is not correct? Both B and C are correct. You have tryptophan, tyrosine as well as phenylalanine. So both B and C will be the correct option here. Okay, the next question. Which of the following statement is or are correct? Yes, tryptophan is also a correct answer. I mentioned that both B and C are correct. Which of the following statement is or are correct? In dialysis, molecules diffuse to the semi-permeable membrane if smaller than pore size. Dialysis is used to remove low molecular weight compounds. In ultracentrifugation, molecules migrate through a semi-permeable membrane under pressure. Or ultracentrifugation. Okay, but if you have to choose only one, then you go for tryptophan, because tryptophan provides even a more high molecular extinction coefficient than tyrosine. So if you see the profile of absorption, you will understand. Also from the structure, you can understand that tryptophan will absorb more because of its you say the pi electron cloud or the uh, ring that it has. Okay. Okay. So what is the answer for question number 12? Which of the following statement is or are correct? So what is question number? What is the answer is saying? In dialysis, molecules diffuse to semi-permeable membrane. That is correct. Dialysis is used to remove low molecular weight compounds. That is also correct. In ultracentrifugation, molecules migrate through a semi-permeable membrane under pressure. And centrifugation can be used to for crude structures. Okay. So yes, 1, 2, and 3 are correct. Good. So is the correct answer. Question number 13. For salting out of proteins, which of the following salts is commonly used? So try to recollect from the Hofmeister series. Good. So option C is correct. Ammonia and sulfate. So ammonium sulfate. Option C is the correct answer. No, you have to choose only one. See, ammonium was at the end of it, and sulfate was also at the end of it. So if you see you use ammonium sulfate, it will also help you in the salting out thing. So try to recollect what I said in the Hofmeister series. Okay, so if you see over here, where is the series? Let me see. See, for salting out, you are using ammonium, and when you are increasing this, it is salting in. So this one is for salting out, this one is for salting out, this one is for salting in, this one is for salting in. So that's why ammonium sulfate. Understood? You have to choose only one. Now also we have ammonia, sorry, sodium, but that is a bit in the mediocre, I mean it's in the medium range. But the highest one is ammonium sulfate. So where did it go? Okay. To determine the size of the protein, which of the following techniques can be used? Which of the technique can you use to determine the size of the protein? Okay, only SDS page, nothing else. If I say it's a multiple uh, choice question, MSQ, multiple choice, what is that? MSQ question, then actually you can use all of these techniques for determining the size. Analytical centrifuge can also be used, but you cannot use size exclusion chromatography. It only tells you about the monomer, dimer, or what? No. It also tells you about the size of the protein, because when you run a control experiment of known molecular weights and then you run your protein of interest, from there you can tell what is the size of your protein. So all A, B, and C are correct. So any of the above is correct. We can use analytical centrifuge, SDS, as well as size exclusion chromatography. Okay, the next question. During a successful purification scheme, it may be expected that the specific activity increases, specific activity decreases, number of proteins in the sample decreases. when you're purifying it, what happens? Actually, the specific activity is seen to increase or decrease. See, first thing is that the number of proteins in the sample decreases because there are a lot of other proteins. But when you're purifying it, you're only having the protein of interest. Out of 1,000 molecules, you have say only 200 molecules of the protein of interest. So ultimately, the number of proteins is decreasing. And now the specific activity is increasing or decreasing. Definitely, the activity of the protein will increase because there are no other impurities or contaminants. Because of that, your protein activity will increase. So your specific activity increases and number of proteins in the sample decreases. So it's correct. Now the next question. Okay, so yes, so this one I think I discussed. Which among the following statements are correct? This is number two. Nuclei have lower density and high sedimentation coefficient. So that is correct. D. Okay, which of the following technique is best suited for estimating the overall secondary structure of a protein? I was just telling which technique you can use for understanding the secondary and the tertiary structures. Very good. It is the CD spectroscopy. Next, what do we have? Okay. So, three-dimensional structure of a protein can be determined by. How can you determine the 3D structure of a protein? Okay. X-ray crystallography. Any other thing? You can also understand the three-dimensional or the tertiary structure of a protein by NMR spectroscopy as well as CD spectroscopy. So all these three options are correct. So CD spectroscopy tells you also about the tertiary structure of a protein as well as the secondary structure of a protein. And NMR and X-ray are mostly for your tertiary structures. Okay, so A, B, C are correct. Now particle size and sample homogeneity can be determined by. So how can you understand the particle size and the sample homogeneity of a particular protein? Using which technique? Okay, for understanding the particle size and the sample homogeneity, you have to run a dynamic light scattering. That is the DLS. From that only you, from there only you can tell about the particle size and the sample homogeneity. The other techniques cannot give you information about the particle size and the sample homogeneity. It can give you about the molecular weight and the size. The last question for today: a protein without any affinity tag is being purified. Which is the best possible strategy for its purification? So, how can you purify a protein that does not have a particular tag from an extract? Okay. Salting out, ion exchange, and ACC. That is the perfect answer. Very good. So that is the right answer. Okay. So that's all then for today. Now, if you have any questions, you can ask me. Yes, you can open your mic and ask me the question. That's not an issue, big deal. And this video is being recorded as well, and I will be sharing the slides. So if anytime you people face any difficulties, you can contact me in this email ID. And ask me questions. If you face any difficulties anytime, I will answer you over mail. Okay. So I think we can then end the class over here. Thank you all for joining. See you in the next week.